applications of AB.
So as the first talk of this session, we have Aruna Goswami. She will be speaking on metal poor stars and galactic chemical enrichment. Aruna Goswami, please.
Hello, am I audible? Hello?
You're audible. A little louder, please. A little louder.
Okay. So, good evening, everybody. I would like to thank the organizers for giving me this opportunity to talk on some of our recent results on metal poor stars. And the results that I'm going to present today are mostly carried out along with my students, Sajila Mal, Meenakshi, Parthapratim Goswami, and Rajiv Singh Rathore. So I'll be talking about mostly the chemical composition studies of metal poor stars. So according to the most accepted theory, the universe started with a gigantic explosion, the Big Bang. The chemical history of our universe began with the Big Bang. So in the first few minutes after the Big Bang, universal cosmological nucleosynthesis formed all the hydrogen and deuterium, some 3 helium, major part of 4 helium, some 7 lithium, leading to primordial mass fractions 0.76 for hydrogen, 0.24 for helium, and for all other heavy elements, it is almost 0. Now, the existence and distribution of the chemical elements and their isotopes is a consequence of nuclear processes that have taken place in the past in the Big Bang and subsequently in stars in interstellar medium where they are still ongoing. Now, over the last 3 decades, our understanding of the galactic chemical enrichment has come from the chemical composition studies of stars belonging to different components of our galaxy, the thin disk, the thick disk, and the halo of our galaxy. The seminal works by McWilliam, Ryan, and Edvarsian, and subsequently by others, gave elemental abundances of stars, and these abundance ratios reveal in principle the chemical history of our galaxy. Now, understanding this or the interpretation of these abundance ratios is not straightforward because it has to be understood on the basis of a appropriate galactic chemical evolution model. And out of the many ingredients, it is only the stellar yields which can be calculated from first principles, and for all other parameters or the ingredients like star formation rate, initial mass function, inflow, outflow, one has to rely on empirical prescriptions. But with the release of the stellar yields, theoretical stellar yields, for a set of large number of isotopes corresponding to stars of different masses ranging from 10 to 40 solar mass and at different metallicities, it has become easy, or it has become possible to compare our observational data with theoretical predictions. Now, very few studies have, of course, explored the full potential of these yields. Now, according to the cosmological simulations that are based on the lambda cold dark matter model of hierarchical structural growth in the universe, the first stars formed in small mini halos some few 100 million years after the Big Bang. The first stars that were formed were very massive, and which is, say, in contrast to today's low mass stars dominating the mass function. So early chemical enrichment of the universe began with the deaths of the first stars at very high redshift. Direct observations of the first stars is not yet possible, but clues to their nature may be extracted from their nucleosynthetic imprints on the second generation stars. So the chemical imprints in the oldest, most metal poor stars can reveal the first nucleosynthesis events in the universe. So there have been many surveys which have been conducted with the prime idea to find out the most metal poor stars. And the spectroscopic method is found to be the best one, and but it involves it is very arduous. It involves three steps. Uh, Firstly, a large sky survey program is conducted at a very low resolution, about 400, where millions of stars are observed and looked for the calcium K and calcium H features. These are metallicity dependent features. So the potential candidates are then observed at a slightly higher resolution, say about 2000, and which is just sufficient to estimate the metallicity of the stars. And the ones which are found to be the bona fide or the actual real metal poor objects, very metal poor stars, those are then studied at a higher resolution, say greater than 40,000, which is just required for doing detailed chemical composition studies. Now, in this slide, so uh, before we proceed, I would like to quickly recall the definition of abundance. The abundance of one element with respect to another is given by this relation. And when we have A for A and B, Fe and H, this quantity Fe by H is used as the metallicity proxy for the metallicity of stars. So by definition, this quantity is 0 for Sun, and an element is referred to either underabundant or overabundant when its logarithmic ratio compared with the same ratio in the Sun is lower or higher, hence negative or positive respectively. So stars in the range with Fe by H minus 7.4 to 0.5 are known, and Beers and Chryslip say they have classified these objects into different classes where stars with metallicity Fe by H minus 1, they are called as metal poor. With metallicity less than -2, they are called very metal poor, -3 extremely metal poor, -4 ultra metal poor, -5 hyper metal poor, and -6 mega metal poor, and -7 septa metal poor. Here we are comparing the spectra of stars with different metallicity. What we are seeing on the top is the spectrum of a solar type stars, so Fe by H 0, and then we have a spectrum corresponding to metallicity -1.6, -3.2, -5.4, and -7.0. Now, what we see here is that the strongest optical ion line, 3860, which is seen as a very strong feature in the solar metallicity star, slowly becomes weaker and weaker. And when we reach -5 metallicity, this feature is just seen like a tiny blob. And for -7, this feature is almost not detectable. So these are the current limitations and observational challenges of metal poor stars. So even though there are metal poor stars which are being found by large sky survey programs, we are not in a position to study them in greater detail because which would require larger telescope equipped with a sophisticated spectrograph. Because, for example, if you look at this object, SM0313, which has a metallicity less than -7, a spectra was taken with an exposure, 13 hours of exposure, signal to noise 120, 35,000 resolution, but you could not even detect this feature. So in future, when the large telescopes will come up with, sophisticated spectrograph, for example, we'll be able to observe an object with magnitude 21 at a resolution 40,000, that would give 200 signal to noise ratio, but with an exposure time for 4 hours. So So the chemical enrichment history of the galaxy is can be understood with the abundance of trends of the elements when we plot them against the metallicity Fe by H. So in this one, we are plotting the titanium, calcium, and magnesium. And in this one, we are showing the ion peak elements, that is chromium, cobalt, and scandium. Now, what we see here is that there are definite trends, say, followed by the metal poor stars. Metal poor stars, say, at a metallicity less than minus 1.5, they are enriched with a value about 0.4 DAX. And at minus 1.5, they become solar, and this is explained by the fact that supernova type 1a begins to contribute to the galactic enrichment with iron at this chemical time. But we see a different trend for the ion peak elements. For example, at a lower higher metallicities, higher than minus 1.5, they show a lower trend, is subsolar values. But for example, scandium doesn't show any trend. If we look at the heavy elements, strontium, barium, and europium, they show large scatter, and these kind of scatter cannot be explained by the systematic differences between individual studies, and therefore it is believed to be the origin is believed to have cosmic origin. So among the metal poor stars, about 30 to 40% stars, they show enhancement of carbon, and they are called carbon enhanced metal poor stars. Surface chemical composition of these stars show products of different nucleosynthesis processes. And way back in 2005, Beers and Chris Leabe have classified the camp stars into different groups based on the chemical abundance of only two elements, that is barium, the representative of S process element, and europium, the representative of R process element. And accordingly, camp S stars are those which show barium by europium greater than 0.5. Camp R stars are those that show enhancement of europium greater than 1. Camp RS, these are the stars which barium by europium has a value between 0 and 0.5. And there are this class of objects called camp no stars. They are carbon enhanced, but they do not show enhancement of heavy elements. Now, over the years, elemental abundances of many other heavy elements became available, and different groups have come up with different classification criteria where they have included the abundances of other important heavy elements. So so based on that abundance patterns, so R process camp R stars, they can also be again subdivided into R1 or R2 depending on the enhancement degree. And there are also, we have these stars that show enhancement of S process elements, and within this range, barium by europium greater than 0.5, barium by lead should be greater than minus 1.5. Alpha element enhanced stars, they show enhancement of magnesium, silicon, and calcium. And it is surprising that some of the very metal poor stars, they show very high abundance of magnesium and silicon, and they are called the alpha enhanced stars. Now, the observed differences in the chemical signatures of the subclasses, they are thought to be tied to differences in the astrophysical sites responsible for the nucleosynthesis products they now exhibit in their atmospheres, including elements produced by the very first generation of stars. Now, in a recent study, what we have done is that we have tried to look if HS by LS, this ratio can be used as a classifier for these camp S and camp RS stars. Now, HS implies that this is the heavy S process elements, and LS implies light S process elements. In this figure, what we are showing is that the number of stars versus HS by LS, and we see that there is a clear overlap of camp RS stars with the camp S stars. So definitely this HS by LS ratio cannot be used as a classifier for these two groups of stars. And if we plot this HS by LS with respect to metallicity, then they show, they do not show any trend. They are all mixed up. So if we plot this European versus HS by FE, then of course you see a very clear correlation. And it shows that this particular trend, it definitely shows that the origin of this camp S stars shown with black and the origin of camp R stars are shown by the red points. They might have the same production mechanism or the same origin. So we have also tried to check whether strontium by barium and barium by europium can be used as a classifier. And what is plotted here is that the red grid, that represents the location or the region occupied by camp R stars as put forward by Hansen et al. And the black ones corresponds to the region occupied by camp S stars. Again, we see that there is an overlap region, so strontium by barium definitely cannot be used as put forward by Hansen et al. As a classifier. But in this picture, what we see is strontium by barium when it is plotted versus europium by Fe. At europium by Fe1, they separate this camp S stars and camp RS stars into two groups. So maybe this is a better classifier. And here we see that barium by europium versus Fe by H, this is the region, the red region is the region which is given by Beers and Krisliev for camp RS stars, but these stars also occupy the region of camp S stars, so that cannot be a very tight criteria for distinguishing this camp S and camp RS stars. Again, if we consider that europium by Fe at 1 and barium by europium, then we see that these stars, they fall into two distinctly. They can be distinguished based on this criteria, which is put forward by Abbott et al. Lanthanum by europium as a classifier was also being examined by several authors, but then we also find that the red grid which occupies the region, shows the region for camp R stars, we see that there are two outliers, one here and one here. So there is a little, uncertainty about this classification scheme. But here, if we consider the Abbott et al. Classification scheme, they haven't put an upper limit for lanthanum by europium, and therefore perhaps maybe a better one. And we have also examined this lanthanum by europium as a classifier, comparing collecting data for a large number of stars, including our estimates. And then we have come up with our classification scheme like this, where we say that europium by Fe, if it is less than 1, then barium by europium has to be greater than 0, lanthanum by europium has to be 0.5. And if europium by Fe is greater than equal to 1, then barium by europium has to be 0, and lanthanum by europium has to be greater than 0.7. Now, this work got just published very recently in January. And other characteristics of these camp stars. So among the camp stars, we have the camp S and camp no stars. They are the most populous. And camp no stars, as I said, that they do not show enhancement of S and R process elements. And they are enriched in nitrogen, oxygen, sodium, magnesium, and other light elements. The most metal poor star that we know till today, that star is found to be a camp no star. And only about 14 stars are known with metallicity minus 4.5. And 85% of them are camp no stars. So camp no stars are likely born very early in the universe and likely to provide valuable clues on the first stars, early nucleosynthesis, first supernovae, and early galactic chemical evolution. Now, in an effort to search for chemical imprints of the first stars, we have conducted low-resolution spectroscopic survey of the galactic high-latitude carbon stars using HFOS attached to HCT with an aim to find the potential candidate stars. And we have subjected more than 500 objects to low-resolution spectroscopic analysis, and we found that about 40 of them CN stars, 2 CJ stars, 20 50 CR stars, and about 160 CH stars. There are some of them which remain unclassified. They do not show enhancement of carbon, and they also do not show the specific spectral features seen in carbon stars. So the results of these studies have been published in different papers. What we have done is that the sample of CH stars we have taken for follow-up high resolution studies, and because this is CH, Camp S, and barium stars, they are binaries with a now invisible white dwarf companion. So they can be used as tracers of AGB nucleosynthesis. So we have performed high resolution spectroscopic analysis for several potential CH and barium stars, and we could characterize the companion AGB stars, their masses, neutron source, and neutron densities using a abundance ratio of rubidium by zirconium values, and this work is published in these first two papers. In the sample, we have also found a number of Camp RS stars that show astrophysical signatures of I process, and we have published those results in this particular work. And what we are showing here is that the abundance astrophysical signatures of S process and the I process. This figure shows the red ones, the solar system abundances, and the dotted ones, that is the model predictions coming from a 2 solar mass evolved star with Fe by H minus 2.3. At low metallicity, therefore, the S process operates efficiently enough to produce S process abundances equal to or greater than the solar system values, including larger amounts of lead with a atomic number 82. Now, in the middle plot, what we are showing is that the red circles, these are the abundances of this particular star LP625-44, a very metal poor Camp RS star. It is fitted with the model predictions of S process, and we can see this cyan color model predictions. And then I process model fit is shown in blue, which is taken from Hampel et al. And we see that and here is the residual with the from the observation. It shows the residual plot is at the bottom of this plot. And in the right-hand side, what we are showing is the I-process model fits for 4 objects that we found as Camp RS stars. And the red points, these are the observed values, and blue one is the model fits, where we have taken the stellar yields from Hampel et al. This is one example where the abundances of the star shows a combination of S process and R process model, R process yields. So here the black points, these are the observed points, and different colors, green, cyan, and magenta. These predictions, they consider metal poor S process pattern along with initial R process contributions. So this is one example where we can say that the surface chemical composition shows the products coming from R process as well as the S process. So in our sample, we have also got a couple of Camp No stars, and these are 2 examples. HE2155 minus 2043 and He 21555, 48 minus 2039. Now, what we see here is that the metallicity of these two stars are same, minus 3.46 and minus 3.32. Carbon abundance differ by a factor of 10. Here it is 6.4 and here it is 7.0. And the carbon, but what we see, a very strange thing here is that the magnesium abundance is 1.54 for this particular object, and it is minus 0.35 for this. Now magnesium, this is an alpha element. So it definitely implies that the alpha elements in these two stars, the source of alpha elements in these two stars must be very different. This star also shows several other anomalies. For example, if we look at the strontium and barium lines, this strontium line is very weak in the case of 2148. It is a very strong barium line, 4934. But in this star, He2155, we have very strong strontium and very weak barium. So this also implies that although these two stars have similar metallicities and very high in carbon abundance, their source of alpha elements as well as the neutron capture elements are very different, and it requires really we need to understand why these stars show very different abundance patterns. But if we look at its position in this plot, AC by metallicity, these are our these red ones are our stars, program stars. We see that they fall into the region which is occupied by camp no stars. Camp no stars are shown in blue here and also by green. Now, these are two different groups of camp no stars. One doesn't show a dependence on metallicity like the green ones, and the blue ones, they show a dependence on metallicity. So one object falls on the blue group, that means showing the dependence on metallicity. The other one, which is marginal at the, or it also falls along with the magenta, the lower limit, the magenta, these are the camp S stars. So perhaps this one, we think that because it doesn't show any enhancement of heavy elements, it belongs to the group which is occupied by this green green symbols. So about the other heavy elements of these two stars, they nicely fit with the abundances of camp no stars that are again shown in blue and green, and the magenta, they show the abundances of camp S stars. There are, examples from ultra-faint dwarf galaxies where they do not show enhancement of heavy elements. This is one example where we are comparing the stellar spectrum of D119, which is a star of Draco-dwarf spheroidal galaxy with a metallicity minus 2.95. It doesn't show the presence of strontium-2 line and also the presence of a barium-2 line, but in the galactic halo star day, they are very strongly seen, these two elements. So the origin of the heavy elements of the stars belonging to the galactic halo and the stars belonging to the ultra-faint dwarf galaxies looks like a very different. So we see the other surprises from ultra-faint dwarf galaxy stars like Reticulum 2. Here we are showing the examples of two objects with metallicity minus 3.2 and metallicity minus 2.7. Although the metallicities are different, the magnesium abundances are very similar, minus 2.6 and minus 2.6. They are underabundant, but they are they show the similar values. So the stars having similar metallicity generally show similar alpha enhancement, but in this case, we see a alpha, alpha element, that magnesium is underabundant for, for the stars belonging to this reticulum too. Now, in here we compare the stars, a spectrum belonging to a star of Segu-2, which is an ultra-faint dwarf galaxy star. And again, the black one shows that reticulum star, and the blue one, light blue, this red one, it shows a star, our process enhanced star of this is a halo giant. So the halo giant and the reticulum, they show similar enhancement of our process element, but this our process element is missing in the case of a ultra faint dwarf galaxy star. So there are a lot of
Aruna, time is up.
Yes. So yeah, thank you. So there are these discrepancies about the abundances of heavy elements in stars, and a lot of studies are ongoing to understand the origin and evolution of heavy elements, not only in the galactic halo stars, but also in the ultra-faint dwarf galaxy stars. So what we see in the Milky Way is that europium by age increases with increasing Fe by age, but in faint classical dwarf galaxies, europium with respect to Fe by age remains constant. So our process, it is a rare process, and there are suggestions that the neutron star mergers may be the producers of our process elements, but then there are certain uncertainties about this production scenario. One is that about the frequency of neutron star mergers, and where it can effectively work at a very low metallicity. So nonetheless, there are some observational evidences which indicate that a neutron star mergers could be a possible site for our process elements. There have been several attempts to understand the abundance patterns that we see in the Camp No stars by comparing with very population tree, very massive stars. And here are some examples. Like you see the dotted red line, it corresponds to 20 solar mass object. The dash, this 32 solar mass objects is shown with green, and the black 60 solar mass. And when you consider the mixing episode and extra mixing to the evolutionary code, then you see that these are shown with solid lines in red, in green, and black. And these circles, black circles, they correspond to the carbon by 12 carbon isotopic ratio values found in Camp No stars. And this solid line, which considers mixing, it goes through, through these points. So indicating that a 20 solar mass objects with extra mixing, the yields of such a system can well reproduce the abundance patterns seen in Camp No stars. However, a lot of work still is needed to understand the abundance patterns of Camp No stars, and a lot of understanding is still remaining. So detailed measurements of the element abundances of metal poor stars with peculiar abundance ratios will provide useful constraints on the existence and fraction of very massive stars in the early universe. So at the same time, we need high quality optical and near UV spectra of known metal poor stars, along with improved atomic data and model stellar atmospheres to better understand the chemical enrichment history, particularly of the heavy elements. So I'll stop here. Thank you.
So I think there is a question on chat. How do you take exposure for order 16 hours for these stars?
Okay, that is actually, they don't take at one go. They take several exposures. of about 40 minutes time, and then they build up, they add the spectra to build up the signal to noise. So, and at the same, and 16 hours, of course, you cannot get it in one day. So maybe 2 or 3 days, but and it has to be observed in the same settings so that we can add the spectrum.
Any other questions? There is this question, any study for O or N in our galaxy?
Any studies? I could not get your...
For oxygen or nitrogen in our galaxy?
Oh, yes, there are several studies actually for this thing. You mean that abundance studies of oxygen and nitrogen? For many of the stars, we do determine the oxygen abundances and the nitrogen abundances. Oxygen abundances are determined from 6300 and 6363 lines, and if they are not visible, then we use the oxygen triplet line. And oxygen triplet lines have non-LT effect, so we also apply the correction factor, and we determine the oxygen abundance using mainly these lines. For nitrogen, we generally use synthesis of CN band, and where we first determine the carbon abundance, and then we use that carbon abundance to determine the nitrogen abundance from the spectral synthesis calculations of CN band. So CN band, you can see around 4 to 15 Armstrong and also around 8004 Armstrong region, CN band are visible. And of course, sometimes if the object is very cool, then you do not see the atomic lines of oxygen, then CO molecular band can be used to determine the abundance of oxygen. For many of these metal post stars, we have determined oxygen abundance, nitrogen abundance, along with carbon abundance.
So there are no other questions. I will ask my question on chat regarding whether the motion of these stars have been checked in Gaia, whether they are from any satellites that have merged with the galaxy or not. So that will come on chat. I thank Professor Aruna Goswami for her talk, and we go on to Swastik Chowbay, who will speak on post-star metallicity of directly imaged planets. Swastik, please share your screen. You can unmute yourself.
Yeah. Am I audible?
You're audible.
Yeah, just a second. So my slides are visible, right?
You have to go full screen. You have to go full screen. Yeah, correct. Fine.
Yeah. Okay. Okay, fine. So good afternoon, everyone. So
12 minutes plus 3 minutes.
Okay, so today I'll be discussing about the host or metallicity of these directly imaged planets. And I did this work with my supervisor Ravinder Banial, as well as my collaborators Mayank and Manoj from TIFR, and Shivrani, Ishwar Reddy, and Rajguru from IIA. So first, the brief outline of my talk will be, I'll be talking about discussing about the exoplanet demography and the different populations of the exoplanet. Next, I'll be telling about why directly imaged planets and why we should be studying these populations and their host star. Then I'll be discussing about the star-planet correlations. Mostly I'll be talking about the stellar metallicity and planet mass correlations. Then I'll be discussing the current work that I have been doing at IIA to estimate the stellar parameters and some of the main results that we have obtained. And then I'll summarize my work. So coming to the exoplanet discovery timeline, after the first discovery of the exoplanet 51 Pegasi b, most of the planet search methods were dominated by the radial velocity technique. But after the Kepler mission, the number of planets detected by transit increased. And as of now, the planets detected by transit methods is almost the 4th time of the planets detected by radial velocity. In this context, the number of planets detected by direct imaging stands 51 as of now, which is much less than the other detected other techniques. And the planets detected by techniques such as microlensing and transit timing variation are also not that much. So Now, looking at the demographics of the exoplanets, we can see that this planet population in orbital period and planetary mass plane can be broadly classified into 6 categories, with the ultra short period planets have orbital period less than around 1 day or less and are quite less massive, less than 0.3 Earth masses. On the other extreme end, we can see the cold Jupiters, which has orbital period, large orbital period more than 100 days, extending up to 10 to the power 5 days, and planet mass more than 100 Earth masses, extending all the way up to 30 Jupiter mass. Now, looking this picture in a slightly different way, we can see that the planets that have been confirmed, the planets that have been confirmed to be detected, directly imaged planets pops up out as a separate parameter, as a separate population in this parameter space. This is because different planet detection technique suffers from selection biases. As we know, the radial velocity and the transit methods are mostly sensitive to closing to moderate orbits, and they host largely the main sequence and evolved stars. Direct imaging, on the other hand, hosts are self-luminous, young and massive planets in wider orbits, and they're mostly hosted by young and pre-main sequence stars. Talking a little bit about the directly imaged planets, as I said before, they are young and warm. They are self-luminous. They are detected mostly at infrared wavelengths. It requires a large telescope and adaptive optics system with a stellar coronagraphy to detect these planets. Imaging and spectroscopy is possible for both the star and the planets. And as of now, a total of 51 planets have been detected and 45 stars by this method. Now it comes to the question, why do we study these directly imaged planet host stars for the planet formation? What information do we get from this? So first of all, these directly imaged planets and the host star together as a population are not well studied, unlike the two other population, that is the radial velocity and the transit population. And before we started this work, the metallicity was known only for 10 out of 45 stars, and they had large error bars, and they're also not determined uniformly. So some were detected. So the technique by which the metallicity was determined was different. So, and the third point is that this directly imaged population sample actually overlaps with the giant planet and the brown dwarf population in terms of the mass distribution. So if we understand this directly imaged population, it will help us to bridge the gap between the two mass regimes of the celestial objects. But then it comes the question, can the stellar parameter or studying the host star properties such as metallicity can provide us any answers to the possible formation scenario of these objects? So now going a little back, in early studies, such as in the coral sample and leak cake sample, it has shown that the initial results showed that the metal-rich stars are more likely to host planets. So, but we have to remember the number of planets. So these studies were done around 2005 by Deborah Fisher. So the Kepler was still not launched. So number of planets detected was not very high to make separate classification for giant planets as well as Earth-like planets or different category of planets. But then still it was clear that the metallicity might play a role in hosting planets. Then after when Kepler mission was launched and several other ground-based observations were taken with large number of giant planets, it became easier to understand the distribution, metallicity distribution for the host stars of these giant planets. Now the question comes, why giant planets? Why are we interested about giant planets? The reason is that most of the directly imaged planets are giant planets, and the minimum mass of the directly imaged planets starts from 2 Jupiter mass. So that's why we are more interested to understand the formation and evolution scenarios for these giant planets only. Giant planets can be subdivided into two categories. One is Jupiter type planets and the super Jupiter type planets. Jupiter type planets are planets with mass range 1 to 4 Jupiter mass, whereas super Jupiters are from 4 to 15 Jupiter mass. Now you can see in the plot on the upper left corner shows the overall distribution, with the blue color showing the Jupiter type planet distribution and the dotted ones showing the super Jupiters. Dividing this overall population into different stellar mass bands, we still find that the distribution of the metallicity of the host stars for the Jupiters are mainly concentrated towards the metal-rich stars. We find a more scattered for the host star metallicity for the super Jupiters. This possibly indicates for a different formation scenarios for Jupiters and super Jupiters. Other studies also for the Kepler planet host, Narang et al. Found that the average metallicity increases as a function of planetary mass, but the trend reverses after 4 to 5 Jupiter mass. But this study was conducted for moderate orbital distances around 0.1 to 10 AU. We wanted to see if this study holds for planets at large orbital distances. And for that, the directly imaged planets are the most ideal candidates. Now, sample selection. For our present work, we analyzed 18 directly imaged planets for which the spectra was taken from Keck and ISO. For the four directly imaged planet host stars, we took the value from literature, and the stars for which we could not do the analysis was either the spectra was not available, or the quality of data was poor, or some of them had are quite hot and have rapidly rotating. So with a large V Sini, we do not have clear spectral features to make reliable estimation. So that's why we are restricted only with 22 targets. So data analysis, usually there are two methods for data analysis. One is the synthetic spectral fitting and one is the equivalent width method. So, and we have used iSpec, which is a Python wrapper, which bundles several radiative transfer code, model atmosphere and line list into a single module to obtain the stellar parameters, both from synthetic spectral fitting as well as from equivalent width method. But here in our case, we used iSpec only to generate the synthetic spectrum. We used Bayesian analysis to obtain the posterior distribution of the stellar parameters. For our analysis, we used the spectrum radiative transfer code together with the Wald-Nile list, and the solar scale was taken from Asplan 2009 paper. So this is a flow diagram which shows that how the stellar parameters were estimated. So we generated the synthetic spectra from the iSpec, and then at every stage we computed, we generated the synthetic spectra from our prior knowledge, and then we computed the log likelihood at every stage, and then at repeating this for a large number of times, we obtained the posterior distribution for these stellar parameters. So let's say for one example I've shown here, so we have taken 40 initial random prior values, and then we have looked into the convergences, and then after 300 steps, when the values converged, we took the distribution and we set the burn-in limit at 140 steps. So now these are the stellar parameters that we have obtained, and this is the metallicity distribution for our directly imaged planet host stars. We can see for 22 stars, our median value is slightly above 0, and the dashed line represents the first and third quartile of the distributions. Similarly, for the metallicity versus planet mass distribution, we can see that most of the metal-rich stars, for most of the planets with low mass have metal-rich stars, metal-rich host. Whereas as the planet mass increases, we see a more of a scattered distribution. The dotted and the dashed line represents the 5 and 13 Jupiter mass boundary here. And the color bar represents the orbital distance in AU. So now we wanted to compare our directly imaged planets population with the short orbit giant planet population. So for that, we selected 552 objects. So 494 planets were taken from NASA Exoplanet Archive and SweetCat. And then we have taken for 58 brown dwarf from BOMA and Gill sample from the radial velocity searches. So our entire sample mass has a mass range from 1 to 80 Jupiter mass, with orbital distance spanning from 0.02 AU to 20 AU. We have used the minimum mass where true mass was not available. And then we perform the clustering analysis using the Gaussian mixture analysis to see where does our population lie with the overall population of the giant planets. So now directly imaged planets host in the larger picture, we see that we find a decreasing in the stellar metallicity planet mass plane. We find a decreasing trend in the average stellar metallicity as a function of planet mass. The directly imaged population cluster lie in between the super Jupiters and the brown dwarf. On the other hand, with respect to stellar metallicity versus orbital distance, we find that a decreasing trend in the average stellar metallicity as a function of orbital distances, and the directly imaged population clusters lie as a separate class of population here. Now I'll summarize what work we have done. So we have used the Bayesian analysis to estimate the atmospheric parameters and the metallicity for 18 directly imaged planet host stars. We have used MCMC technique to obtain the posterior distribution of the stellar parameters using model spectra generated using iSpec. We found that the For the low mass giant planets less than 5 Jupiter mass, they tend to have metal-rich hosts. This is in line with the predictions of the core accretion theory. For higher mass planets, we find that the metallicity of the host stars show usually a scatter, and the metallicity might not play a very crucial role in formation of this giant planet. This is again with the agreement of the gravitational instability model. The direct image population clusters lie as a separate class of objects in the stellar metallicity orbital distance plane. And in terms of stellar metallicity planet mass plane, we see that it lies in between super Jupiters and brown dwarf population as expected. So that's all I wanted to say. Thank you if you have any questions.
Thank you. Questions, anybody? When you are using a Gaussian mixture model, you are assuming that these three form physically, for some physical reason, they form separate populations.
Yes.
So,
yeah.
At the same time, they seem to show a sequence also. So, to the massive Jupiter and the 1 to 4 and 4 to 15 Jupiters, what is the physical separating mechanism?
Okay, this plot, right? Can you just, okay, so why they are separated, like why they are separate population, that's the question, right? In terms of mass plane. In terms of mass plane, right? Okay, so what we understand is that these celestial objects, they have different mechanism in formation. So you believe that the planets around 4 Jupiter mass, they are formed from by the core accretion process, right? Where a solid core is formed first, and then if in the formation process, and if there is sufficient gas, then it accretes the gas onto its surface and forms the giant planet. On the other hand, the planets in between from 5 Jupiter mass to around 15, 20, 30 Jupiter mass, it's more likely that these are formed from the disk instability. So once you have a disk, then the disk collapses gravitationally, and then you have then it forms as a separate entity as a planet. The last category, which we haven't shown here in much details, is the separate formation from cloud collapse. So for the brown dwarf, which are higher than around 30 Jupiter mass or somewhere, they are most likely to form from the cloud collapse process, just like the stellar binaries form. So it is more likely that it can form in that way. So it could be the reason. So we have not explored the brown dwarf population yet.
Thank you so much.
Yeah.
So thank you for a very nice talk. We will go on to the next speaker, who is Manami Roy, speaking on gamma ray and radio background constraints on cosmic rays in the Milky Way circumgalactic medium. Manami Roy, please share your screen.
Can you see my screen?
Yeah. Now go. Yeah, full slide now. It's coming out well.
Okay.
12 minutes.
Hello everyone, I'm Manami Roy. Yeah, okay, thank you. Hello everyone, I'm Manami Roy. I'm a graduate student at Raman Research Institute. I'd like to share with you a recent work that has been done by our group, me, Ronita Jana, and our supervisor, Biman Nath. This work has been published recently in AB. We investigated well-debated issue of how much cosmic rays are there in the Milky Way circumgalactic medium with the help of gamma ray and radio background observations. Well, circumgalactic medium or CGM is a region between galactic disk and intergalactic medium, which is filled with very diffuse gas. You all know that ISM has typical density of 1 particle per cc, where CGM has particle density approximately of 10 to the power minus 3 to 10 to the power minus 5 particle per cc. Now you can imagine how diffuse the CGM is. My mental picture of CGM is like a cupboard of a not so very organized person. So if we see the cupboard from outside, we kind of see a peaceful, quite organized thing. But if we open the door of the cupboard, we can see the real mess. Similar is a CGM. if we look overall at it, it seems to be a very quiet place. Seems like not much things are going on. But when we zoom in and focus on the small details, we can see a lot of mess going on there. Inflowing, outflowing, recycling of gas, and many more. These messy processes are very important in galaxy evolution, and this makes CGM a very, very important lab to study galaxy evolution. Now, question is, how do we observe CGM? In the case of the cupboard, where it's very easy to see the messy details, we just need to open its door. Unlike that, details of CGM is very hard to observe, as it has very low density and emission measure is proportional to density square. It's really difficult to observe in emission. But no need to worry. Observation of absorption lines come to the rescue here. So continuum from the distant quasar suffers absorption from the different metals and ions of CGM. And from these absorption feature, we can tell out messy stuff going on in the CGM. So metals and ions have their own favorable temperatures. Like for O7, it's 10 to the power 6 Kelvin. For Mg2, it's 10 to the power 4 Kelvin. The observations of absorption lines from such different ions are seen in these spectra. This point to a wide range of temperature structure of the CGM with hot, warm, and cold phases from ranging from 10 to the power 4 Kelvin to 10 to the power 6 Kelvin. The coexistence of these phases implies that there are roughly in pressure equilibrium. So we expect the cold phase to have a higher density compared to the hot phase if we only consider thermal pressure balance. But as you can see here, the density obtained from the observations of a cold phase tends to follow the hot gas density profile. This means that there is a contribution from some non-thermal pressure component. And one of the possible candidates for this is cosmic rays. The question is, how much cosmic rays are there in the CGM? The cosmic ray particles are either accelerating the disk and then advected outwards or produced by acceleration in the out. Once these high energy particles are lifted to the CGM, they diffuse throughout the halo. Recent numerical simulations of galactic outflows have shown that the CGM can be significantly populated with cosmic rays. According to these simulations, the ratio of cosmic ray pressure to thermal pressure, eta, can vary widely, ranging from 1 to even 100 for different transport mechanisms. One can ask, is it something from the observations? The answer is yes. We can't see wind, but we can detect its presence by seeing moving leaves. Similarly, we can't see cosmic rays, but we can detect its presence by their moving leaves, which are photons.
Manami, we have lost you. Your slide is not visible to me.
Yeah, she seems to have dropped off.
Hello, Manami, we have lost you. Hello.
I got a message from Naren saying that he's trying to call her and get back.
Okay, meanwhile, shall we go ahead with the next speaker? She can join later.
Okay. So the next speaker is Gargi Shah, is it?
Yeah.
Okay. So for then Gargi Shah, then I'll have to pay the YouTube video.
Right. Shall I announce?
Yes. Okay.
So we will continue with Manami Roy's talk after the other two talks are over.
Sorry, Indulekha, I think Manami.
Oh, Manami Roy is back. Yeah, please continue, Manami.
Indulekha, you have to make her a co-host. She
Yeah,
can't.
I'll do that. She can unmute herself.
Yeah, now I can do. Sorry for the network glitch.
That's fine. Please carry on. Yeah, your slide has restarted.
Cosmic ray protons interact with CGM protons and produce neutral pions, as you can see in the picture. So these neutral pions immediately decay into gamma ray photons. On the other hand, cosmic ray electrons interacting with CGM magnetic field produce synchrotron emission in radio band. Hence, we can track the cosmic ray in the CGM with its two indirect tracers, the gamma ray background and the radio background. We use Fermilab data for the gamma ray photons and RK2 balloon-borne radio observation data to compare our model with observations and constrain the cosmic ray population. To calculate the gamma ray and radio flux, we need the density and temperature profiles for CGM. So we consider CGM to be in hydrostatic equilibrium under the dark matter halo potential. There are two widely studied analytical models for the CGM. One is simplistic isothermal model, where CGM temperature is held constant, and the precipitation limited model, where we consider the ratio of cooling time to free fall time to be constant. So there are two main players in this game of precipitation limit. One is cooling, another is gravity. The tug of war between the time scales of these two processes gives us this limit. Let us see how. If a region becomes dense compared to its surrounding, cooling time of that region becomes smaller than the surrounding. As you can see, the cooling time is inversely proportional to the density, so it cools faster than the surrounding gas. And as there is small scale pressure equilibrium, cooling makes that region even denser, which further increases cooling. Cooling stops only when the gas cools below a temperature at which radiation cannot be emitted efficiently. Now, another player, gravity, comes into play. Gravity, due to dark matter halo, would decide whether a cold gas can condense out of hot CGM or not. Recent numerical simulations show that cold gas will precipitate out of hot gas if the ratio of cooling time to free fall time is roughly less than 10. The cool block will sink into the medium due to buoyancy because it is denser than the surrounding. And if the ratio of cooling time to free fall time greater than 10, then before the cold blob can cool to a stable temperature, it will get mixed with the surrounding gas due to its motion relative to the surrounding. If the ratio is less than the threshold value, then blob can get cooled before gravity makes it get mixed. Thus, cold clouds condense out of the hot CGM gas. So CGM maintains a threshold value of roughly 10 to the ratio of this cooling and free fall time scale at which this multi-phase condensation becomes possible. So with the dotted line in the left panel, we show the isothermal model, and in the right panel, the precipitation model. And we modified these two models by including non-thermal cosmic ray component, taking eta, which is cosmic ray pressure by thermal pressure, as a parameter. So this results in suppression of thermal pressure. That means density, temperature, or both for CGM models. And the solid lines here shows the profiles with different values of eta. That means different value of PCR by P thermal. It turns out that the modified models satisfy the density and temperature constraints from different observations. So density constraints from the different observation, like you can see here. Can you see my cursor here? Like, okay. So
I can just see the cursor.
okay, so it's like from HVC density constraint and from temperature constraint from the recent observations of NGC 3221. So this is the temperature profile a recent study has got. So using these temperature and density profiles, we calculated the radio and gamma ray flux. The radio synchrotron flux does not constrain the isothermal model, but puts an upper limit of eta less than equal to 400 for the precipitation model. And we then calculate the gamma ray flux at a particular frequency. The figure shows that the isotropic gamma ray background flux puts an upper limit of eta less than equal to 3 for the isothermal model and eta less than equal to 230 for the precipitation model. But there is a twist here. The off-center position of solar system in the Milky Way gives rise to an anisotropy in this gamma ray background. The anisotropy, when compared with the observed value, says that eta should be greater than 100 in the precipitation model, and it rules out any cosmic ray population in CGM for isothermal model. Therefore, our work shows the importance of the calculating the gamma ray and radio background in order to constrain the cosmic ray population in CGM, and we think it would be really interesting to produce the gamma ray and radio map for the outflow and CGM simulations. That's it. I will leave you with this summary of our work, and thank you very much for your attention, and sorry for my network connection. I would be really happy to take questions now.
So thank you, Manami. Any questions? Shri Kumar? Okay.
Thank you.
Please unmute.
A quick question on the comparison of the gamma ray background is done with the Ackermann paper. And I noticed very quickly your slide went by very fast. I thought it said it's at 3.85 GeV.
Yes.
So you've taken the flux, the gamma ray background at 3.85 GeV?
So yeah, in their paper, they have actually divide their flux in different beam. So we have chosen the one beam, and we have taken the mid energy of that particular beam and calculated our gamma ray flux for our model.
Pi naught contribution that you expect would show up at a different energy, correct?
Yeah, so
that is because at 3.85 you will have other contributions potentially, including inverse Compton. So
yeah,
you want to strictly compare. Yeah, go on.
For inverse Compton, the time scale would be larger than the diffusion time scale. So,
but the number that you derive from the Ackermann paper at 3.85 is inclusive. It's not purely the pi naught component, but it's pi naught plus other components. So what you will have to probably do is fit the additional spectral components and only take a value that is corresponding to the pi naught contribution at 3.85.
Yeah.
Alternately, you could actually go lower in energy from the full spectrum and take a number that may be more appropriate for your comparison.
Right. Okay. But I think when we are taking the gamma ray flux from all the contribution, like as you have mentioned that it has all the contribution, so it kind of give a upper limit of gamma ray flux in the model, and
but you could tighten it even more, is what I'm saying.
Yes, that we can done. It can be done. Yeah. We will check that.
Any other question? If not, we thank the speaker for a nice talk. And Manami, could you please stop sharing your screen?
Yeah.
We go on to the next speaker. Yeah, thanks. Who is Gargi Shah? Gargi Shah, ionization rate in the galaxy. So Gargi Shah, please. She's not audible.
I had to unmute my Zoom. Sorry about that.
Yeah.
First, I would like to thank SOC and LOC for giving me chance to talk today. Thank you. And here is my talk.
She's not visible now.
Yes,
Yeah,
yes.
now
Sorry.
visible. Fine.
Sorry.
You have to go full
First,
screen.
I would like to thank SOC and LOC for giving me chance to talk today. Thank you. And here is my talk. So, yeah. Today, I will talk about role of polycyclic aromatic hydrocarbons on the cosmic ray ionization rate in the galaxy. Though the name is cosmic rays, but cosmic rays are high energy particles, mostly made of protons, whose energy ranges from a few MeV to a few GeV. Low energy cosmic rays, whose energy is less than 10 MeV, are very efficient in ionizing hydrogen. However, the flux of low energy cosmic rays cannot be directly observed. These cosmic rays, they play an important role in the interstellar medium. They penetrate deep into the interstellar clouds and produce a primary ionization and a second basket of secondary ionizations. The free electrons they produce heat the gas, and deep in the cloud, they control the ion molecular chemical reactions in the absence of other ionizing sources. Several groups had estimated the value of cosmic ray ionization rate Xi based on the abundances of various molecules whose formation depends on the cosmic ray ionization. So based on HCO+, Van der Tat and Van de Schop, they have estimated a value 2.8 plus minus 1.6 into 10 to minus 17 second inverse. However, based on the H3 plus observation, McCall et al. Have estimated a much higher value, 3.5 into 10 to minus 16 per second inverse. Based on H3 plus observation, Neufeld and Wolfire, they also estimated a higher value, 5.3 plus minus 1.1 into 10 to minus 16 second inverse. So the value of Xi differs depending on the molecule involved. Among all these molecules, H3 plus has the simplest chemistry. It starts with cosmic ray ionization of H2. So H2 plus here goes to H2 plus. This H2 plus reacts with H2 and gives H3 plus. Now H3 plus get dissociated via the electronic dissociative recombination process into 3H or one molecular hydrogen plus another hydrogen atom. In the steady state, the formation rate is balanced by the destruction rate. So this is the Xi. H2 is the cosmic ray ionization rate of molecular hydrogen. This is the density of H2, electron density, H3 plus density, and K is the electron recombination coefficient rate. For a constant density cloud with length L, this number density can be written as column density, which can be observed. Now, the K was also measured in laboratory by Oka and McCall. However, this electron density that cannot be observed directly. So various groups, they have used simple approximations. So McCall et al., they have assumed that all electrons are produced by the ionization of carbon to C+, and they approximate the electron fraction, that is Ne by NH, to Nc plus by NH. They also assume a constant value for the electron fraction, that is 1.4 into 10 to the minus 4 for all of their calculations. In addition to these, they also assume the molecular fraction to be 0.67. So based on these simple approximations, H3 plus observations and H3 plus observation along 50 site lines, McCall et al., they have estimated a value 3.5 into 10 to the minus 16 per second inverse. So the question is, how accurate are these simple approximations? These site lines, they have PDR structure. So to test the uncertainties, we choose one standard PDR model, F1, and here are the results. So along x-axis, we have plotted AV. Along y-axis, we have plotted density. The yellow line is the electron density. The blue line is the C plus density. And this red one is the CO. Black one is the H plus. Green is S plus. And the cyan is H3 plus multiplied with 10 to the 4. So now we can clearly see that the electron density is not equal to the C plus density. The ionization of hydrogen, sulfur, and other metals, they contribute to the electron density. And the radiation field, presence of pause also contribute to the electron density. And in the second plot, we have shown the H3 plus density along x-axis and the electron fraction along y-axis. We can see that the electron fraction is not constant. It drops drastically where H3 plus forms. So then we decided that, okay, we will do detailed numerical simulations. And for that purpose, we used Cloudy. And Cloudy is a widely used spectral synthesis code designed to understand complex physical environments building from a foundation of atomic and molecular processes. It determines the physical conditions within a non-equilibrium gas exposed to an external source of radiation, and it predicts the resulting spectrum and column density using a very few number of input parameters like density, chemical composition, radiation field, geometry, and a suitable stopping criteria. So we choose 9 site lines, and we choose those site lines where the density has been estimated using the rotational levels of C2. We did this because we wanted to reduce the error in our models. And for these site lines, the E, B minus V are also measured. These are the observed H3 plus column density with plus minus 1 sigma and H2 column density with plus minus 1 sigma for these site lines. So we assume the plane parallel model. As I told you, density is derived from observed C2 levels. E, B minus V is observed, and we the extension of the clouds are set by the observed value of E, B minus V. We assume the standard ISM gas phase abundances. We also assume MRN size distribution for grains.
Hello.
And we specify the radiation field in terms of the standard galactic having radiation field. So then for each site line, we run a grid of models with varying radiation field and Xi-H in a step of 0.5x. Now, pHs, they are very common in the galaxy. They have a structure of, they have benzene-like structures, and the number of carbon atoms vary. Thielen's has observed that the abundance of C atoms locked up in pHs containing 20 to 100 carbon atoms are 14 parts per million each atoms. And these pHs are very important because they absorb electron very effectively. So the electron density depends on the presence of pHs. However, the very little is known about the presence or absence of pHs along these site lines. So based on Thielen's observation, we considered 3 different pH abundances, and we denote that pH high, pH average, and pH low. So here are So due to the lack of time, I won't be able to show all the plots. I will just show few of them. And our results has been accepted for publication in ABJ. So anybody interested can see our work in the ADS. So here, these are contour plots. So along x-axis, we have plotted the cosmic ray ionization rate in log scale. And along y-axis, we have plotted the radiation field in log scale. The black solid lines represents the column density of H3+, and this gray field area is observed H3+ column density with ±1 sigma error. Similarly, the blue lines represent the contour plots of H2 column density, and this cyan, field cyan area represent the observed H2 column density with ±1 sigma error. We estimate the cosmic ray ionization rate from this overlap, where these two overlap. Now the difference between this, the left-hand side plot and the right-hand side plot is that here in the left-hand side, we didn't include any pHs. But in the right-hand side, we have included average abundance of pHs. We can see that the overlap has moved to left. That means the cosmic ray ionization rate has decreased when we added pHs. Similar trend has been observed for other lines. I will just show quickly few lines, side lines, HD110432, and this is lambda set, similar pattern. So when we included the pHs, we get lesser cosmic ray ionization rate. So here is the result. So these are the 9 side lines. These columns represent our work with different pH abundances. So this is for pH, high pH abundances. This is average pH abundances. This is low pH abundance. And in this case, we have not included any pHs. So we can see that as the abundances of pHs decreases, the cosmic ray ionization rate increases. So here is the summary. So the common assumption that all electrons are contributed by C+, where H3+ forms, is found to be not correct through this detailed calculation, including microphysics. We also found that the total electron density is affected by the ionization of hydrogen, sulfur, and other metals, and by the effects of pHs. We predict the average cosmic ray ionization rate Xi-H2 with 3 different pHs abundances. So with high pH abundances, we got value 6.5 ± 3.06 into 10⁻16 second inverse. With average pH abundance, we got 7.88 ± 2.89 into 10⁻16 second inverse. And with low pH abundances, we got 75.08 ± 39.90 into 10⁻16 second inverse. So when we lower the pH abundances, that is, lots of free electrons are available. That's why the cosmic ray ionization rate is also high. And when we do not include any pHs, so there are many free electrons, and the cosmic ray ionization rate using the H3+ calculation is also very high in 95.69 ± 46.56 into 10⁻16 second inverse. And we also noticed that the side lines along which have higher EB minus V, they predict smaller value of Xi-H2. And this trend has been observed by Neufeld and Wolfire also. And our results can have interesting implications for low energy CRT spectra. Because a large scatter, we see a large scatter in the cosmic ray ionization rate based on the abundances of pHs. So a large scatter in the value of xi-s2 does not necessarily require a large scatter in the low energy CR flux. The chemistry of the ISM, that is the pH abundances, can reproduce this. So that is the important thing. Thank you. And last but not the least, anybody in the audience who wants to use Cloudy for their own calculations, if they have spectroscopic data and they want to use Cloudy, I'd be happy to help them. Please send me an email. Thank you.
So we thank Gargi Shah for her talk. So any questions to Gargi Shah may be based on Slack. And we go on to Supriyo Ghosh. Supriyo will be talking to us about the characterization of cool giants from low resolution near infrared spectra. Supriyo?
Yes,
Please.
yes, I'm sharing my screen. But
it is not yet come through. It's not yet come through.
But I could not able to share my screen actually.
Dipanjan, maybe shall we put on the PDF? Yeah, it's coming, I think.
Okay.
Right, you have to go full screen now.
So full screen is visible or?
It is not full screen. It's
okay,
visible,
so
but
just
not in full screen.
Just a minute. There is some problem and
Supriyo, as you had tested earlier, why don't you share the desktop?
yes, but I cannot able to share the desktop actually. So entire screen I could not able to share.
Yeah.
Supriyo, you can try it once. Otherwise, I can share your screen and you can just tell me to when to change slides.
Just a minute. Yes, now I can able, I think.
Dipanjan, you are being.
Now the screen is visible or I think so. Hello?
The process.
Yes.
I think.
Hello?
Yes, Supriyo, we can see your screen.
It's visible.
Okay, thank you. So hi everyone. And today in this presentation, sorry.
Please be fast because we need this Zoom channel for the GBM, general body.
Okay, sure. So I will try my best at, okay. So in this presentation, I would like to talk about how we can characterize cool giants from low resolution near infrared spectra. So the basic idea of this work is to establish empirical relation using the well-characterized sample stars. Then these empirical relations can be implemented to derive the stellar parameter for the unknown star. So in this way, we can actually start understand and classify different galactic and extragalactic environment. Also in this presentation, I will show how the Bayesian inference can be implemented to derive the systematic between the two data set, and also how do we establish the empirical relation. In addition to that, I will be presenting preliminary results of our ongoing projects on Kepler red giants based on observations from newly install instrument TANSPEC on 3.6 meter telescope at Devastal. So let's start with a brief introduction. So cool star basically represents the post main sequence star in the RGB and the AGB phase. So their typical temperature below 5000 Kelvin and the spectral type are K and M. More importantly, if we see the K-band spectra of the cool giants, a number of prominent atomic and molecular features are visible, which can be used to characterize those cool giants. Now let's see how the spectral feature depend on the stellar parameter. So in this figure, we can see the line strength significantly changes with the stellar parameter. Therefore, we can use the strength of the spectral feature to constrain the stellar parameter. So the main motivation of this work is to provide easy to use diagnostic tool for the cool giants. The beauty of such diagnostic tool is that we can easily derive the stellar parameter by only measuring the line strength of the spectral feature. And also we do not need any information regarding the reddening or the distance to the object. So for that, we obtain 260 cool giants from archival spectral library, and our sample actually spans over a wide effective temperature and metallicity range, ensure that we can establish empirical relation for wide metallicity range, and also investigate the possible metallicity dependence on those empirical relation. Now to calculate the line strength, we calculate the equivalent width. However, before calculating the equivalent width, we actually degrade the spectral resolution to the test spec resolution, that is 1200, because we are interested to study the cool giant in low resolution from the low resolution spectra, because it will give us an idea how precise the stellar parameter can be estimated from the spectra of a low resolution spectrograph like T-spec, TAN-spec. And then in near future, we can use these Indian facilities to study the cool giants. So to calculate the equivalent width, we use this formula where F is the flux density inside the feature bands and Fc is the flux density in the continuum band pass. Now, first we investigate whether there is any resolution effect on equivalent width computation or not. So for that, we actually calculated equivalent width before and after degrading, before and after resolution degradation, and we found that there is no significant resolution effect on equivalent width computation. Now, this equivalent width we use this equivalent width for further study. First, we study the behavior of the spectral features with the parameter. Now, from this figure, we can see all the spectral features studied here have strong dependence on the effective temperature and the metallicity. Now, from the correlation matrix, we found that that CO at 2.29 is the best indicator for effective temperature, while sodium is most sensitive to metallicity. Now, before establishing the empirical relation, it should be noted that we use two different data sets. So if we look the figure very closely, we can see that NIFS and X-shooter data occupy dissimilar paces in certain parameter space. So this could be because of the systematics of the dataset. So first we need to investigate the systematics of the two dataset. So in the absence of any common star between the two data sets, we use Bayes' theorem for the first time to estimate the systematics between the two data sets. So this is the mathematical formula of Bayes' theory, which actually estimates the conditional probability. In Bayesian analysis, in general, we follow the following steps. So first, we need to identify which parameters are to be predicted and which parameters are supposed to act as a predictor. Then we define a descriptive model for our data that is relevant for our research work. In our study, we consider the regression equation that may be linear, quadratic, or cubic. However, the model is not complete yet. We have to describe the random variation of our variable around the predicted values. So for that, we consider that our variables like X or Z here, our variables are randomly distributed according to the normal distribution and to the predicted variables. For Z, it is Zm and with a standard deviation sigma Z. Now, in this way, Bayesian analysis enables us to incorporate the measurement error in the analysis. So for linear equation, the probabilistic reformulation of the probability reformulation is shown here. And now we need to consider the systematics term. So for that, we add a new term, that is beta digit nifs. So we set that beta value is 0 for X suit. That means we consider our model predicted X suitor values are our model predicted values, and we estimate systematics only for the nifs data set. Now, in the third step, we need to specify the prior distribution of the model parameter. So this is actually the schematic view of the Bayesian model for the linear regression. Now, coming back to the prior distribution on the model parameter, we also consider that the model parameter also are distributed randomly according to a normal distribution. Now we need to define the mean and the standard deviation of the model of the normal distribution. So for a linear equation from previous study and also from looking at the data set, it's very easy to define the mean and the standard deviation for slope and the intercept. However, in absence of any common stars between the two data set, to calculate the mean and standard deviation for DJ or the systematic term, we compare different literature, and from there we estimated the mean and standard deviation for effective temperature and for the metallicity. So to calculate the systematics, actually we consider the overlapping region where the two data set are overlapped, and in that overlapping region they show a significant linear tense. So we consider the linear regression formula, and then we use this prior distribution. So now our model is ready. Now we implement this Bayesian model in PyMC3, that is a Python package to fit the model. And here I am showing the model fit and the posterior distribution of the systematic term. Now from the posterior distribution, we actually estimated the systematic offsets between the two data sets, which are listed in this table. Now we use this systematics value to establish the empirical relation. Now we use this prior distribution and we'll consider the whole data set and to calculate the to establish the empirical relation, and following the similar method as described earlier, and we found that the linear fit is provide the best result for effective temperature calculation. However, the cubic fit gives the best empirical relation for the metallicity, and the posterior distribution of the model parameter are also shown. So the summary of the posterior distribution are listed in this table. Now, so from here we found that the accuracy of our empirical relation is 150 for effective temperature estimation and 0.25 dex for the metallicity. Now we are interested to investigate the metallicity effect on our effective temperature empirical relation. So for that we actually divided our data set into three groups. One is subsolar, another one is solar, and the supersolar. And then we established the empirical relations following the similar method, and we found that the empirical relation based on the subsolar or supersolar metallicity significantly deviates from the empirical relation and of the solar stars. So from here can conclude that we need to be very careful to estimate the effective temperature for supersolar or subsolar star, because otherwise there will be a large uncertainty in effective temperature estimation. Nonetheless, we can use if we use very carefully the empirical relation, we can easily derive the stellar parameter by only measuring the line strength. However, in this work, we do not consider the evolutionary status of the red giant. So these study are likely to be biased by the selection effect. So we studied the Kepler giants having the clear having the distinct evolutionary status. Now thanks to the Kepler and Corot mission, now the red giants can be classified into three classes. One is normal red giant, red clump, and the secondary red clump star from the using the astroseismology. So our aim in this project is to do the spectroscopic follow-up observation and more covering the whole optical to NIR region. And in this process, we also test our established empirical relation. However, our ultimate goal to investigate whether we can able to distinguish this evolutionary status from low resolution spectra or not. So for that, we select the Transpec instrument for our study because it is a unique instrument which unique spectrograph which provides simultaneous wavelength coverage from 0.5 to 2.5 micron. It has two mode of observations. One is XD mode, that is high resolution mode, and another one is low resolution mode or prism mode. So that low resolution mode can be used for sky survey because of its high throughput. This instrument also consists of an independent imaging camera with a plate scale 0.25 arcsecond. Now we use the high resolution mode for our study, and we use slit 1 arcsecond because the better signal to noise ratio, and we can observe 7 Kepler giants, and the some of the spectra are shown here, and we can see a number of prominent features of the red giant stars, and we also calculate the signal to noise ratio of those giant stars. Now we consider the K-band spectra and estimate all estimate the strength of the spectral feature and estimate the stellar parameter using our established empirical relation and compare it with the literature. And we found that for some cases there are very good agreement and large deviations are seen for other cases. Now we need to investigate all the possibilities with a handful number of sources before draw in any conclusion. And also we are exploring other bands like H band or J band to cross-check our derived stellar parameter. And for just to note that the Transpec data reduction pipeline is in progress, and it will be made available publicly very soon. So here is my conclusion here. What I'd like to say that I give a very overview of our work. So details can be found in this paper. So thank you. Hello.
Divya, you have to make Indulekha a co-host.
Hello.
Divya, are you there?
Yeah, sorry, just give me a minute. Sorry. Yeah.
Hello.
Yeah. Yes, my apologies, Indulekha. So please carry on. Yeah.
Yeah, it's okay. So thank you, Supriyo. If anybody has any questions, please raise your hand. So while you are deciding on your question, can I ask a quick question? So was this particular Bayesian method checked for robustness against changes in prior, and how far can you push this method? Like, if the Gaussian's normal distributions are broader, how far can you push it?
Sorry, I didn't get your question. So you are asking about how far we can push the prior distribution, or?
No. How sensitive is the treatment to the prior?
How sensitive for the systematic terms, or the other terms, like intercept and the slope term?
There are two parts actually. You have assumed Gaussian distributions for the parameters.
Yes.
So they are broader. Will this still work? That is one question. The other question is, how sensitive is this Bayesian method you have using to the priors which you are assuming? Have you changed the prior and seen what?
Yes, we have changed. We consider for slope and the intercept, we consider the broad priors. Here you can see, here it can be seen. But it is very sensitive to the for the systematic term. If systematic term would be larger, then there will be a established empirical relation will be different. So it is very much sensitive to the systematic term, but not for the slope and the intercept term.
Okay, thank you so much. Any other questions? There are no other questions. If there are anybody wants to ask any more questions, they may be posted on Slack channel. So with that, we come to the end of this second of the sessions on stars, interstellar medium, and the galaxy. And we thank all the speakers for this session: Aruna Goswami, Swastik Chowbay, Manami Roy, Gargi, and Supriyo Ghosh. With that, we close this session and hand over to Deepanjan. Deepanjan, if you have any announcements, please. Thank you, the audience, for your patient listening. Bye.
Yeah, thanks to the chair and the entire audience.